Hey guys, welcome back. So last time we talked about when we were finding the distance, how we needed to know the distance so that we could tell how much energy the star was putting out. So if I have a really bright star, is it bright because it's putting out a lot of energy, which would mean that the planet would need to be really, really far away? Or is it just bright because it's close? Now you know how to find the distance to the star. Once we know how to find the distance to the star, now we can actually figure out how bright the star really is. And that's called its luminosity. So we're going to talk, the luminosity is how much energy the star is putting out, and that's ultimately what I want to know. Now I'm going to introduce a couple of different concepts with that, but basically if we know the distance and we know the apparent brightness, how bright it seems to my eye, that's called the flux that we receive from the star, the flux of light that we receive from the star. I can measure that. I just turn my telescope up and I look at it. Simple as that. If I measure the parallax shift, I can get the distance. So if I know the flux and I know the distance, now I can figure out how bright that star really is. Is it bright because it really is bright, or is it just bright because it's close? All right, let's get started. All right, so this tool is called Finding Luminosity. And again, just like with finding distance, every time you are doing a problem or you're working on your final or anything like that, you say, oh, I need to find the luminosity. You simply go back, find the one that has the title, Finding Luminosity. And it walks you through all of the theory and everything that you need to get down to the final equation that you need. All right, so go ahead and pull your class notes out. That's going to be Finding Luminosity. Looks something like this. Front and back of one page, as always. Pause the video until you're ready to go. All right. So we want to measure how much energy that star is putting out because we never lose sight of our goal. We want to find a habitable alien world. We want to find aliens we can talk to. So that means I need to know what's the temperature on the planet. In order to know the temperature of the planet is getting all of its heat basically from the sun, from its star. So in order to know how hot the planet is going to be, I got to know how hot that star is going to be. So I need to measure that energy output. Now, there's no way that I can measure it directly without actually traveling to the star, which right now we can't do. But take a look at the brightness here. So if this is our star, when I'm 1 unit away, let's call this 1 AU, 1 astronomical unit. So this would be the distance from the Earth to the sun. So all of that energy may be concentrated on one square right here. Now, if I go 2 AU away, the same amount of energy. Remember, all the energy is in that cone and it's spreading outward. So that energy is now spread out not over 2 squares, but actually over 4 squares. So it's the distance squared. As I go to 3 AU away, it's not just spread out over 3 squares, it's spread out over 9 squares. So you see that the further away I go, the fainter the star is going to appear. This is why, even as bright as the sun is right now, if we go out to Mars, the sun starts to look much, much, much dimmer. And if you go into Mercury, it's going to look much, much, much brighter. So, since there's no way for us to directly measure the star's energy, we're going to get a smaller and smaller fraction of it as we move away. So this is why things look dimmer when they're farther away. It's not that the light is weak or tired or anything like that. It's just that it's being spread out. And so it's just like you take butter and you spread it out over just a small amount of butter over a larger piece of bread, it's going to be thinner and thinner in any one part of the bread. So we're only receiving a little part of this. So here's some terminology that we're going to talk about. I mentioned this in the opening. The luminosity is how bright the star really is. This is its actual brightness. All right, and we measure that in watts per second. So, or I'm sorry, in joules per second, which is a watt. 1 watt is the energy per second. So the total energy emitted by a star every second, that's the luminosity. Now, watts, it's a big number because it's a star. You know, you may have 10 to the 18 watts or something like that. Well, that's way too many numbers. It's hard for us to kind of, as humans, to wrap our brain around. So a lot of times we're going to compare this to solar looms, solar luminosities. So the sun is one solar loom. If I have a star that's twice as bright as the sun, it's putting out twice as much energy as the sun, that's 2 solar looms. Isn't that easier than using a whole lot of zeros and things? If it's putting out half as much energy as the sun, that's half a solar loom, zero point 0.5 solar looms. So if it's putting out 10 times as much energy as the sun, it's 10 solar looms. So this is a nice, convenient measure. Sometimes we will have to use watts and we will have to convert back and forth between them. But for the most part, during this course, we're going to be talking about everything in solar looms. All right, now this is an intrinsic property of the star, but that means it's a property of the star itself. It never changes. It's like your eye color. Your eye color is an intrinsic part of who you are. You can't just change it on a whim. So that would be an intrinsic property. You can't measure it without actually traveling it to the star, though. That's the disadvantage. So now the flux is how bright the star seems to my eye or my camera. So that's its apparent brightness. So that's the amount of energy we are receiving from the star every second. And we measure that in units of watts per square meter. So if you think about it, you've got a square meter that's basically 3 feet, a little bit more, a three foot by 3 foot square. However much energy we have shining on that every second, that's how much apparent brightness it is. For a star, think about it. If I've got a big square that big, say I've got just a big black piece of cardboard, and the light from a star is shining on that, how much energy do you think that's putting out? Tiny, tiny, tiny bits of flux. So your flux is always going to be a tiny number. It's going to be 10 to the minus 7, 10 to the minus 10, something like that. It's going to be a really small number. However, how much it actually is depends upon our distance. Now, our sun puts out over 1,000 watts per square meter because we're very close to it. But even the closest star to us, Alpha Centauri, is so far away that we're getting just a tiny, tiny little fraction of it. But how much we get then depends upon the distance. The farther away from you are from the sun, the less energy that you're going to get. But this is something we can measure on Earth. So I can measure the flux, but that's not what I want. What I want is the luminosity. However, if I measured the flux and I also know the distance, then I can get the luminosity. So let's see how that works. So let's do some comparisons here. So let's say we've got 3 stars here: Akhenazi, Bade, and Cicero. These are not real stars; they're totally made up names that are conveniently called star A, B, and C, and so that's what we're going to call them. All right. So look at your questions in your class notes. Which star is actually brighter, A, B, or neither? Pause the video and think about that. So if we're talking about actual brightness, are we talking about the luminosity, or are we talking about its distance? Okay, we're talking about its luminosity. So this is its actual brightness. Both of them are the same brightness as the sun. So in this case, the answer is neither. They're both one solar load. They're exactly the same brightness. Do you see that? So they're both the same brightness as the sun. All right. Which star seems brighter from Earth? Star A, star B, or neither? Pause the video and think about that. Okay, so we know that in reality, they're the same brightness. However, star A is 10 light years away, whereas star B is only 5 light years away. Which one's going to seem brighter? Since Bade is closer, since star B is closer, it's going to seem brighter just because it's closer. Does that make sense? Okay, now, which star seems brighter from Earth? Star B or star C? Pause the video and think about it. All right, so they're the same distance away. So the stars are right next to each other. They're both 5 light years away. But star B is actually one solar loon, whereas star C is only 0.25. Well, if they're the same distance away, which one's going to seem brighter to us on Earth? Well, that's going to be star B because it really is brighter and they're the same distance. Star B would have to be a long way away before it would start to seem dimmer than star C from that. Okay, so that's a little exercise. And if you're not sure about that, pause the video here and kind of go back through it because you need to understand this concept before we go any further. All right, so notice that the amount of energy that we receive goes up as the star's brightness goes up. So if the luminosity goes up, it seems brighter from Earth. So those are directly proportional, which means that the luminosity has to be in the top part of the equation. On the other hand, as the distance increases, the flux that we get goes down. And so those must be inversely proportional. And so distance goes in the bottom. However, notice that it's actually worse than just the distance going down. It's the distance squared because 1 squared is 1, 2 squared is actually 4, 3 squared is 9 from that. So that's why I have this squared here. You see how we're able to build an equation just from noticing what we see out in the sky? So that's where most of the equations you see come from. So we've got this, and I want to solve this actually for the distance. So I'm going to move distance to the other side, and then I'm going to be left with the luminosity. So I'm going to have the luminosity is equal to the flux times the distance squared, and then to make it equal, this it's not exactly equal. I need some constants in there. Right? Let's see if that makes sense. So we started with our original. Our flux was equal to the luminosity divided by the distance squared. I'm going to multiply both sides by the distance squared. So that cancels here. And so the luminosity then is going to be equal to, and I've got some constants in here that I haven't worked out yet, the flux times the distance squared. Okay. If you can do that, that's all the algebra you're going to need for the whole course. That's basically it. All right. So this could be a good equation for finding the luminosity from the flux and the distance. But the thing is that I can't measure the distance directly, right? So it would be faster if I just put this in terms of distance, in terms of parallax, that is. But you guys know that the distance is equal to 1 divided by the parallax. So I'm going to take this 1 divided by parallax and I'm going to put it in here for the distance. And so when I do that, I get that the luminosity is equal to some constants times the flux divided by the parallax squared. So that's my formula. As the flux goes up, the luminosity goes up. As the parallax goes up, though, the luminosity of the star goes down. Now, to figure out what those constants are, that's when I need to do some observing. So I just hand this over to the observational astronomers. They look at a whole bunch of stars. They figure out what that pattern is, and they figure out what that number is. Where that constant comes from, we don't actually need to worry about. Just know that it comes from observations. That's it. Okay, so now we're ready to write the tool in its final form. And that's going to look something like this. Its luminosity is 9.94 times 10 to the 6th times pi. If you have a pi button on your calculator, use it. Otherwise, you can just use 3.14, and that's fine. Times flux divided by the parallax squared. Now, real important that you remember, whenever you put in 9.94 times 10 to the 6th, you are not going to put it in as 9.94 times 10 raised to the 6th. Never, never, never. Always put that in as 9.94 EE6, and then times pi times the flux in watts per square meter and divided by the parallax squared. All right. So you're going to use this anytime you need to find the luminosity, which is going to be a lot. Finding the energy of the star is going to be one of the main things that we need to know, because a lot of the other properties of the planet depends upon how bright the star is. So now the flux and the parallax angle are always observational properties, so it's not something you can calculate. So it has to be given to you. I'm not going to make you sit at your computer for 6 months actually measuring the parallax angle as it goes across, things like that. So the flux, you would normally just point a telescope at it, you measure how much flux you get, and you're done. So I'm going to give that number to you. Same thing with the parallax angle. Now will always give you the parallax angle, not the shift. So you will not have to divide it by 2. All right. So if it just says parallax, that means it is the parallax angle. Do not divide that by 2. All right, so now we're going to do a practice problem. This is Procyon. This is an actual star in the sky. Its parallax is 0.286 arc seconds. The flux is 1.84 times 10 to the minus 8. That's very, very tiny, 0.00000000184 watts per square meter. Well, it's a star. You're not going to receive a whole lot of light on that piece of cardboard. What I want you to find is the distance in light years and then the luminosity in solar lums. So pause the video, sit down, pull out your calculator, work it out. Let's see how you do. Okay, you ready to go? Excellent. All right, so let's do it together. So we need to find the distance in light years. So our light year formula, if you don't remember how to do that, go back to the finding distance formula, and that's how you can get the explanation. But here's our formula right here. So our flux is going to be, our parallax, it's going to be 1 divided by 0.286 is the parallax. And 1 divided by 0.286, I am getting 3.5 parsecs. See if that's what you're getting. 3.50 parsecs. So you see that fourth digit is a 6, that rounds up, and then of course the 9 is going to round up again. So 3.50 parsecs. Are we done? No, I don't want parsecs. I want light years. So I've got to convert it. So I've got to multiply it by 3.26 so times 3.26. And I'm getting 11.4 light years. So light from Procyon left 11.4 years ago before it reaches us. So 11.4 light years. Now I want to find the luminosity. Okay, so I'm going to use that formula down there. So I'm going to do 9.94 EE6 times 3.14 times the flux, which is going to be 1.84, then EE, and then you need to use the negative sign, the plus minus key. Or it might be a minus in parentheses, just depends on your calculator, 8. So it's going to be put in something like that. And then divide by the parallax squared, not the distance. Look very carefully. You see that the P is actually parallax, not distance. You're used to just, filling stuff in straight across. Don't do that. Stop and think. So we're going to divide this by, let's see, I'm going to start over. 9.94 e to the 6 times 3.14 times 1.84 e to the minus 8. And then I'm going to divide by 0.286 squared. And I get 7.02 solar looms. So that means that Procyon is 7.02. It's about 7 times as bright as the sun. All right, that's how much you figure. So it's a really, really big bright star. So if you're not sure how that worked, if you're still struggling with that, stop the video, try it again. If you still can't get it, come by live help because you're going to need to do this for your homework. So you want to get some help with that. All right, so luminosity then is the actual brightness. It's how bright it really is. Flux is how bright it seems to my eye, how bright it seems here at Earth. In order to get the luminosity, I can only measure the flux, so I need to know the distance from the star. L, the luminosity, is measured in solar looms. F, the flux, is measured in watts per square meter, and the parallax, of course, is measured in arc seconds. And then here's our new tool, written in red here. This would be a good time to be following along with your equation sheet. It's also a very good time to start setting up your Excel spreadsheet so that it'll do all this for you before you have to start tackling it in your homework. All right, that's it for this one. Go ahead and download the Finding Luminosity practice sheet, fill it out, work it out, scan it, and submit it. Now, one thing I do want to call your attention to on the practice sheet, there are the first 2 problems after you work out a bunch of math. The first 2 questions have say, without doing any math. You should be able to answer those questions without doing any math at all. And I want your explanation to not reference math. You're not talking about math. You're talking about how big something is or how small something is from that. Okay, so be real careful when you're doing that. All right, so you've learned how to find the brightness of the star, how bright it really is, how much energy it's putting out. That's its luminosity. We're going to start using those terms through here. You're going to start applying that in the lab as well. Remember that I need to know the distance and I need to know how bright it seems to my eye. Once I get that, then I can get the luminosity. Right now, we're measuring everything in solar looms. We'll be doing that for a while. Eventually, we're going to need to convert that into watts. And we'll talk about how to do that conversion when the time comes. But for now, just getting it in solar looms is going to be fine. And just remember, solar looms is relative to the sun. If it's 2 solar looms, it's twice as bright. If it's half a solar loom, it's half as bright. Simple as that. All right, we'll see you next time.